We start with a new chapter, electrostatic potential and capacitance. Okay? Now, if you remember your class 11th, then we had studied two things there. The first was the concept of a conservative field. Okay? It was the concept of conservative field. Okay? Conservative field. And what is a conservative field?
No matter what path it takes.
No matter what path it takes, the work done is the same in moving from one point to another. And we had seen that gravitational field is a conservative field. Fine. So the first definition was that the 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 work done in moving an object from a point P to a point Q is independent of the path, is independent of the path taken. Okay? There was another fallout of that. And what was that? That if I go around in a closed loop and come back to the same point, the work done is zero. So it was something like this. So for here, if say this is point P and say this is point P and say this is point P and this is point Q, then whether you go like that or you take a straight path or you go like that, okay, whatever you do, you'll do the same amount of work. So it depends on the end points and not on the path taken. Okay, that is, it depends on the end points, right? Now if the work done in going from here to here is W, then in coming back on any of these routes or any other route, it will be minus W, something like that. Okay? So if I start from P and go to Q and I start from Q and come back to P, then while going I do the work W, while coming back I do the work minus W, the net work done is zero. So that is the second definition. That is the fallout of this. This is nothing independent. Okay? Work is a scalar. Why? Work done is negative in what sense? When you do not have to do the work. For example, while taking a brick up, you do the work. While getting it down, you do a negative work if you do not want to accelerate it. If you do not want to accelerate it, then you will be pulling it up. Otherwise, if you leave it, it'll accelerate, right? So if you want to bring it back, then you have to apply a force opposite in the opposite direction. Say if the mass is m, then that force is mg, and you have to gradually take it down. So you do a negative work. Your force is upward, your displacement is this, downward, the angle is 180, the work done is fs cos theta, so it is a negative work, right? It's not because it's a vector quantity. Because in one case you are doing the work, in another case the system is doing the work, right? The system is pulling it. So work done in moving an object around a loop is equal to 0. Okay. Okay. And then the third fallout was, if you do work against the system, then it gets stored as potential energy. So you will be able to define a term called potential such that minus dV upon dx is equal to f of the system. So a function Vx can be defined in such a case so that fx is equal to minus dV upon dx. So what happens in case of, say, a potential gravitational potential field? I have a block, mass is m. I apply a force in the upward direction, mg, move it up by a distance h. What is the work that I do? mgh. Obviously this force has to be infinitesimally greater than mg, so that the acceleration is infinitesimally small, so that it will never acquire a definite velocity, and it will take an infinite amount of time in going from here to there. Suppose that time has already lapsed, okay, theoretically, and theoretically it has lapsed, and we go from here to here and we do this amount of work.
What is V?
V is the potential energy of the system. Okay, this is the potential energy of the system, in the sense that, okay, we can define a function this such that minus dV upon dx is equal to
Force applied.
force applied. So what happens if this is my VH, okay, or I move a distance, say x, then this is mgx, so that this becomes a function of x. Now minus ddx of v is equal to minus mg. And what is minus mg? Minus mg is the system force. You see, this is my system force, downward direction. Okay, I have taken the upward force as positive, okay, so downward force is negative. Okay, so it gives you the system force. Now your electrostatic field that we have studied is also a conservative field. Okay, the electric field is also a conservative field. If it is a conservative field, then all these three postulates of or requirements of being a conservative field get satisfied by it. You understand? All these postulates get satisfied by it. Fine? It gets satisfied by it. Normally what this should be is u. Okay, this is potential energy and not potential. Okay, where u, I should call it u. Okay, not v yet. However, in your class 11th, this thing they have used the notation V. Perhaps that is playing down my mind. So, but I prefer to call it potential energy. U is potential energy. Okay, let it be potential energy. This is a potential energy. Okay, and it is here that you'll for the first time understand the difference between potential energy and potential. Okay, potential. And it is an important thing to understand, because the moment you understand it here, you also understand it in case of a gravitational field. Okay, okay, this is called potential. So fine, we'll go to that place, we will go to that topic, but first this. So electric field is a conservative field, so all these three will be satisfied, right? There was another conservative field that we had studied in class 11th, that was the spring mass system, right? The spring mass system was also a conservative field as long as the surface on which it was gliding was frictionless. Okay, so I say that spring mass system or a spring force. Okay, spring force is also a conservative field if we neglect the frictional or damping forces. Frictional or damping forces.
Damping forces, friction.
Damping forces are that the dissipative forces. Damping forces are actually dissipative forces. Okay, you can call them dissipative forces. What are they? For example, it is not always essential that the spring mass system moves like this. It could also be something like this. No, moving in air. But even in air, if it keeps moving, suppose I leave it here, I pull it here and leave it, what happens? If the surface is frictionless, it keeps on going back and forth about the mean position and it will not stop. Okay, so what happens? The amount of work that it does in going from this extreme to that and back to this will be zero. But not so if there is a friction, because some of the energy gets wasted in overcoming the forces of friction, and due to that, if the first extreme was this, then it will come here, then it will come here, then it will come here, and gradually we find that it stops. So there it is working in a loop, it comes back to the same position, but the work done is not zero. There is some definite work done. For if there was no work done, okay, if it was absolutely zero, then it should have come back to the same position, no energy wasted. Understand? Here also, if the damping forces of air was not there, then we'll find it going up and down till infinity, till you actually stop it. But that also does not happen. Why? Because it gets dissipated in overcoming the viscous drag, Stokes law. Okay, it is moving in a fluid. Air is a fluid, right? And what is happening? That is a damping or dissipative force, because you cannot retrieve back the energy that it has dissipated in overcoming the forces of friction against the air molecules. Understand that? Okay, so the same spring mass system or the same gravitational force under some dissipative force is not a conservative field. Okay, but somehow for our purposes, for study purposes, and in order to understand it without making it too complicated, we keep on we keep on harping on the fact, we keep on emphasizing the fact that the movement is non-dissipative. It cannot dissipate, right?
What about the pendulum?
The same thing, the same damping. Otherwise, that would also have been a, because that is moving under a gravitational force. So it would have been moving in a conservative field, and it would have dissipated no energy had it not been engaged in overcoming the forces of friction, back and forth, back and forth. And due to this, what happens? If there is a dissipative force, then the longer the path you take, okay, the longer the path you take, more is the work that you do. So you become path dependent also. You understand? That is the whole concept. If I go from here to here by the shortest route in a frictional field, then I'll reduce, and then I'll waste less amount of energy.
ये असली में नहीं होता conservative.
No, pure conservative field is a hypothesis. But if we are able to make things very, very non-dissipative, maybe a very, very smooth surface, then approximately you tend to that place, right? And then you start introducing these dampings. It is quite possible to do that. Somehow the tools that are required to understand those are not with you at this point of time. But in graduation level, you'll go ahead and say, if you understand what Laplace transform is, then it becomes very, very easy to inculcate these damping forces. It's not a big deal. Okay, and gradually, as you move to the graduation level, you'll be taught that. If you are in an engineering scenario, then you'll be always taught that, because that is how the real systems behave. Fine. So you know the real thing, you know the ideal thing, and then you insert the deformities. Get the point? And that's how it works. Fine. So electric field is a conservative field, so it'll follow all these things, and we should be able to define a thing called potential energy there as well. Okay, there as well, and that's what we'll precisely do next. Okay. Okay, fine.